Swayam Prabha. Digital India. Educated India.
The students, and then eventually after that you never stop asking questions. Okay, I don't know how I will do that, but he will join you tomorrow. Okay, so he's, for personal reasons, unavoidable personal reasons, he's away. Okay? Now I want to tell you a little bit about general things. You are all from class 11. You had a textbook which talked to you about the atomic structure. It told you about the developments in the last century, about how Schrödinger came up with a new equation which explains the atomic structure much more thoroughly and without any gap, and that we have to solve that equation all the time for various systems to understand the behavior of that system. So that is something all of you have done. Was thermodynamics part of your first year course, 11th standard? So you also had the laws of thermodynamics, the first law, which is the conservation of the total energy of the system, that the energy of the universe is a constant, except that it can be converted from one form to the other form with the equivalence established by the corresponding phenomena. Mass to energy is, of course, the famous relation that Einstein came up with, E is equal to mc square as an example. And all other forms of energy, the conversion is equivalent. But then thermodynamics also told you that while the first law says that the total energy is constant, it said the second law is there is a quantity which, for the isolated system or the universe, there is a quantity which never decreases from what it was before. Do you remember what that is? It's called entropy. Okay? Entropy is not energy. Entropy is, at a given thermal equilibrium, entropy is defined in a certain way, but entropy multiplied by the temperature has the dimensions of energy. Entropy itself is not energy. Therefore, the second law tells you that there is something that constantly grows or stays constant but never decreases if the system we study is completely isolated system. For an isolated system, there are no surroundings. For a system, there can be surroundings. For an isolated system, includes everything. For an isolated system, the entropy is a non-decreasing quantity. And then the third law tells you in thermodynamics that if you have not studied, how to calculate that entropy with some reference state. And the reference state is the Nernst law, which tells you that for perfectly ordered crystalline materials at absolute zero, the entropy is taken to be zero. Okay? The reason for that is the other famous equation in physics. We will write down all those equations one by one. That particular equation was put forward 60, 70 years before Schrödinger put down his equation, or 2 years before Max Born and Heisenberg, Werner Heisenberg, came up with another way of explaining quantum mechanics. That happened in 1920, 25, 26, when quantum mechanics in the current form that we are using has been arrived at. Before that, there was something called old quantum theory, which explained the different phenomena with the different approximations and different assumptions. But one of the famous proponents of that theory, Niels Bohr himself, was very unhappy generally with the state of quantum mechanics until that time. And Niels Bohr said, obviously, what he had done and followed by his other very famous scientific colleague and who was also the teacher for Heisenberg, Sommerfeld, Arnold Sommerfeld, came up with a model for the non-spherical atoms, hydrogen atom or atoms with more than one electron. Okay? And so Sommerfeld's model was there. There was then earlier the theory for quantization of the energy, quantization of the angular momentum, starting from the energy quantization of Max Planck. But these were all individual, what you call, observations which fit a certain experimental phenomenon and explained them very well, so that it was clear to physicists that the classical mechanics and the classical physics, electromagnetism, electricity and magnetism united by Maxwell, the classical theories and the statistical mechanics which came up for explaining thermodynamic observations from the microscopic structure of the molecules and atoms or ions or plasmas which constitute a system. If you want to understand why thermodynamics gives you certain numbers which are largely observation in our scale, macroscopic dimensions, if you want to understand them from the structure of the molecules which constitute that system, that science is known as statistical mechanics, which explains at the molecular behavior why these things give rise to macroscopic properties. Okay? So all these things were known, but some phenomena where people were very uncomfortable. Photoelectric effect was, Einstein came up with a radical view which was not accepted before for 100 years after Huygens first said light is a wave, and before that light was a particle for Newton. Okay? And then light became a wave, and then we observed diffraction phenomena, we observed interference, and then we found out that what we call as a wave is not necessarily a wave all the time. Sometimes particles also have behavior like the waves, and waves also behave like particles. So it was a very confusing picture, but people believe that by 1900 most of physics was to be discovered, had been discovered. Okay? Most of it. Little did they know that quantum mechanics was right around the corner. Okay? And that was going to change the whole story. And afterwards, many other things. If that was the state of physics at that time. What about chemistry? You would be surprised that a large number of very distinguished scientists in the 19th century did not believe in the atomic hypothesis. They believed in that there is no necessity for the atoms to exist or the proposition of the atoms to exist. Remember, Dalton came up with this model in 1810, 1820, around very early in the 19th century. And then many experiments were done. Gas laws were discovered. Gases were discovered. Oxygen was discovered. Nitrogen people knew. Then much later, helium and other gases were discovered. And therefore, the matter was not 4 items: earth, water, fire. What is the fourth one? Yeah. Earth, air, water, fire. It was not. The 4 items did not, 4 quantities did not. At least in our cultural system, there were considered to be 5 of them, not 4. Prithvi, Apu, Teyu, Vayu, Aghasam. 5 quantities, we believe. But then, please remember, Dalton had already suggested that materials are broken up to the finest and the smallest pieces. Indivisible matter is finally the atom or the molecule, and then each quantity had unique molecular structure or atomic structure. And then Mendeleev came up with a very beautiful way of filling up these things based on their properties. How systematically their properties varied from one end to the other end, namely from purely, very reactive to very inert. Very reactive being lithium, sodium, potassium, magnesium. If you come down, they're all very reactive metals. And then the very inert, at that time I think argon was known and helium was known, but probably many other things were discovered later. Okay? The point is, Mendeleev had filled up a periodic table and left gaps in between, saying that there are different types of atoms. And each atom is characterized by the atomic weight. Mendeleev filled it up based on the atomic weight, but later it was corrected that it is not the atomic weight that matters, but it's the atomic number which matters. The atomic weights can vary, and also the same atom does not have to have same atomic weight irrespective of what the atom is, but we had isotopes. Therefore, for hydrogen, we had deuterium as another isotope, and for every element, an isotope which simply differed not only in the atomic weight, but not in the atomic number. And the atomic number being the number of protons in the system, and the atomic weight being the sum of the protons and the neutrons together. Therefore, the isotopes were basically differing in the number of neutrons, and all these things were simultaneously discovered by chemists. Organic chemistry had been discovered by Yeah. So the idea was that chemistry parallel developments are happening. Organic chemistry had been discovered. Until then, what was organic could not be synthesized in the laboratory. They were all basically real live materials which were naturally existing ones. So organic chemistry had been discovered by 1900. I am told from one of the indices that up to 100,000 compounds were known. And therefore, at that time, people believed that atomic hypothesis was not necessary. And these were not people who were any low in physics or chemistry. They were very distinguished physicists and chemists at that time. And so there was a lot of confusion around that time. But then in the last 20 years, I would say 150 years from 1850 onwards, the developments have been so phenomenal that we have now come to a point again when Steven Weinberg wrote a book called The Dreams of a Final Theory. Very famous book. I think it is part of your the book collection that you have in the textbook section that you have. Okay. I said I needed some chalk piece. Yes. Thank you. I know one author, I think he's the only one, probably, Nobel laureate. And Abdus Salam and Weinberg theory is the Nobel laureate. Nobel Prize was shared by Steven Weinberg with, I think, Abdus Salam. Then, what is the meaning? We are very close to understanding all of science and all of physics, all of chemistry, just like we were close in 1900. And then came only some irritant phenomena like, photoelectric effect, black body radiation and small things, ignore them. We'll solve them, okay? And then came quantum mechanics, statistical mechanics, and then came the computer, okay? Destroyed all semblance of what we knew. I mean, today, if we go back to find out what we knew up to 1900 is a minuscule of what we know today. Between 1900 and 2024. Okay, so but even with all of that, the field has some really fundamental cornerstones, which fortunately have not been turned around by anybody. They have not been turned. One of the cornerstones is the most favorite one for me is by Ludwig Boltzmann. And the equation is, okay, S on this side is the entropy. Of whatever system that we study. And omega on this side is the number of microscopic arrangements of a system consisting of n particles. N particles. And Boltzmann obviously had this constant which bears his name. It's called the Boltzmann constant. Do you remember what its value is? Any of you? Around approximately 1.38 into what? Into 10 to the minus 23 joules per Kelvin. Okay? Joules per Kelvin. That's a constant that Boltzmann came up with. And Boltzmann had contributed to the whole of the kinetic theory of gases along with Maxwell, James Clerk Maxwell. And of course, you have studied the kinetic theory of gases. That was the foundation for the understanding later of a whole new field called statistical mechanics. And kinetic theory of gases told you that gases have some fundamental properties and their velocities and in thermal equilibrium are distributed. Not all molecules have the same velocity, but some molecules are more higher velocity, some molecules are colder. But on an average, when you say thermal equilibrium, the velocity distribution is given by a formula. And that formula was derived by Maxwell and Boltzmann, thermal equilibrium. But the point is that therefore molecules have different microscopic states. Molecules which have higher velocity belong to a different state. And in a container, molecules may arrange themselves. Is it possible for a container? Imagine two scenarios. If we have two containers which are closed and then connected by a wall, molecules at very high velocity, and that is, the temperature is very high, much higher than the temperature of the other container, molecules with low velocity. And if you now open the container, what happens? After some time, you imagine that both the containers have the same temperature. Okay? After how much time? Measurably finite time. I mean, the difference is not measurable. It takes infinite amount of time for any equilibrium to set up. But the difference between 99.99% of the equilibrium versus 99.9999 is so small that we ignore. Okay? Equilibrium, the approach to equilibrium takes infinite amount of time, but immeasurably finite amount of time, because we can't measure those small changes much. Okay? Now, does this ever go back to a state in which after some time we get back to the original state? That is, high velocity, low velocity. Does it ever go back to that? What is the probability that it will go back to? It's not zero, by the way. Probability is not zero. That is a finite probability, except that is extremely small. We never see that. And there is a device which is supposed to do that by sorting out molecules which are traveling very fast and taking all of them to one side. And then the device will ensure, yes, Maxwell's demon. Okay? But that's a imagination. Okay? There is no real Maxwell's demon. This one spelling, the other spelling is this. Maxwell's demon. Okay? That doesn't happen. But that's also an arrangement. Please remember, molecules here have some arrangement, molecules here have some arrangement, and after you remove the barriers, the molecules go across each of the walls. The fast ones go towards the slow ones are hit by the fast ones, gain speed, and they probably move towards that. After all, the molecules are colliding with each other and colliding with the walls, and therefore, finally, an equilibrium is established. And that equilibrium tells you that there is a thermal state in which there is no further change observed. And that is called the thermal equilibrium. Okay? So, therefore, there are molecules have multiple microscopic arrangements. The number of such microscopic arrangements subject to a given initial condition, finite volume, finite temperature, one volume, one temperature, and one N. That number of arrangements is what is in this formula. Okay. S is the entropy which is connected to this formula, and this number is a number with no dimensions. Therefore, the dimension of S and the dimension of Kb are the same. S is, that's why I said S is not energy, S is energy per temperature. Okay. So, if you have a lot of energy at a very high temperature and you have a small amount of energy at a very low temperature, it's possible for the S at lower temperature be much larger than the S at higher temperature. Okay, it's possible. Okay, therefore, S is connected with energy through temperature or through thermal equilibrium. The only quantity which thermodynamics came up with, it did not worry about the microscopic state of the individual molecular species. The laws of thermodynamics were based on macroscopic observation. And the computation of S is microscopic because now you use the microscopic state. How do you calculate this? You calculate this using quantum mechanics, using Schrodinger equation, using Heisenberg's equations, whatever it is, the quantum mechanical laws tell you, including the statistics of the possible arrangements, this can be calculated using quantum mechanics. This is thermodynamically measurable quantity. Suppose S is about, let's imagine S is about 100 joules per Kelvin per mole at about, say, 300 Kelvin. We'll keep that, okay? Therefore, S at per molecule, if you have to calculate S per molecule, will be approximately what? Divided by the Avogadro number, right? Right? 100 kilojoules, 100 joules. So 100 divided by 6.0223 into 10 raised to 23. Okay? So the number is of the order of 10 to the minus 23. Okay? This is minus 23. Sorry, this is Avogadro number, so 10 to the 23. 6.023 into 10 to the 23. So this is of the order of what? 10 to the minus? This is about 10, 20. So you can say of the order of 10 to the minus 22. Okay, roughly. Okay, per molecule. Now, Kb is already of the order of 10 to the minus 23. So what is ln omega? This should give you 10 to the minus 22 per molecule. Yes, per molecule. Yes, per molecule. So if the ln omega has to be of the order of 10, omega has to be of the order of what? 10 raised to 10. It's 2.303. You can multiply 2.303. So if you want to write this, you can write this as 2.303 log omega. So omega is 10 raised to 10 for a single molecule. What does that mean? 10 billion arrangements for a single molecule. Now, if you calculate S in terms of the mole, and you have a mole of gas in a small volume, what are the number of possible arrangements for that system? Let's take S to be 100. Let's not divide this by the molecular ratio. Okay? Let's take 100 joules per Kelvin per mole. Now, this is on one side, and on the other side you have 1.38 into 10 raised to minus 23 ln omega. Now tell me what omega is. Roughly of the order. What should be omega? Okay. So make it 2.303. log 10. Small number, large number, very, very large number, much larger than Google. What is Google? 10 to the 100. Okay. This is 10 to the 100. And where are we here? This is 10 raised to the Avogadro number. Roughly order of magnitude, ballpark figures. Okay? 10 to the Avogadro number. So, chemists knew much bigger numbers than data scientists know. Okay? Or data scientists could imagine in terms of data points. In one small part of 1 mole of a gas, okay, let's make a large volume, 22.4 liters. We'll do that so that its atmospheric pressure means 0 Celsius. 1 mole of a gas, ideal gas, occupies 22.4 liters. Okay, 22.4 liters has how many microscopic arrangements? 10 raised to the Avogadro number of microscopic arrangements. You see how microscopic behavior, it's not possible for us to look at every atom and every molecule to see what is the macroscopic behavior. The macroscopic behavior is the average of all these microscopic interactions. And the mechanism by which these averages are calculated, that average calculation is done by the field called statistical mechanics, of which Professor Bala is an extremely well-known international expert. Ask him all the questions. Okay? But what is important for us is that a macroscopic quantity thermodynamically can be calculated from a microscopic arrangement of the atoms and molecules in a container, subject to some conditions, constant volume, constant temperature, constant number, if you put that in. That's called an ensemble system, and that ensemble is known as canonical ensemble. Okay? N, V, T constant. When we study that system statistically, that system is known as canonical ensemble. So, using that method, it's possible to calculate macroscopic quantities from the microscopic averages. And there are laws for doing that, and these laws were discovered over the last 100 years by various statistical mechanics, including Boltzmann to begin with, and then Willard Gibbs, who came up as the most famous statistical mechanist of the last century. He wrote a fantastic book. The first famous book on statistical mechanics was written by Josiah Willard Gibbs. And Gibbs is very, you must have seen Gibbs free energy, I'm sure you have heard of in your thermodynamics course. It is the same Gibbs who came up with what is called energies freely available from the system outside of all work and so on. So, one fundamental equation which connects the macroscopic world to the microscopic world is the Boltzmann equation. Okay? Is a fundamental equation in science. It connects the real world to the atomic world. The reason is, from the entropy, through the derivatives of entropy at constant against volume or against pressure or against temperature, we can calculate all the other forms of thermodynamical quantities like the internal energy, enthalpy, or the changes in the internal energy, changes in enthalpy, changes in the Gibbs free energy, changes in Helmholtz free energy. All of them can be calculated if we know what the S is. Therefore, it is possible for thermodynamics to start with S as a starting quantity. Such a formulation was initially not done. Everybody started with the first law, then they put in the second law, and then the third law. But then much later, when thermodynamics mathematically could be understood, it was possible to see that S is the functional function of functions for calculating all thermodynamic quantities. And therefore, the real connection between the atomic world and the macroscopic measurable quantities, everything that we have in our real world, goes back to the days of Boltzmann. Okay? So this is one fundamental equation in science, which you must read more and more, and probably you will find them everywhere as you go up in your higher education ladder. Okay? Of course, now, the most fundamental equation in the last century was credited to two people, okay, or two groups of people. One is Max Born, Werner Heisenberg, and Pascal Jordan. In fact, the equation was written by Born and Pascal Jordan, but Heisenberg was the initiator of this whole idea. He came up with that method, and the equation was known as interesting. I don't know how many of you have seen this equation. Is it there in your atomic structure textbook? No. Q is the position of a particle, quantum particle, position coordinate of a quantum particle. And P is the momentum of the particle, momentum coordinate, momentum value. And QP, the product of Q and P is not the same as the product of P and Q. This is meaning that Q and P have a special role. They don't have the same meaning that you have in your classical object when you say my position is this, or my momentum is 10 kilometers. Mass multiplied by my velocity. My mass is 70 kilos, 80 kilos, and my velocity is 10 meters per, or maybe 2 meters per second, fast running. So I can calculate my momentum, I can give my initial position, and no. That is good, but in quantum mechanics, P is very different. P is given by minus I h bar, the derivative of the position coordinate. Okay? This is what was arrived at by Max Born, Heisenberg, and Pascal Jordan. And this equation is in the tombstone of Max Born. His symmetry, the tombstone has this fundamental equation. Okay? Max Born was the scientific mentor, advisor to Heisenberg. Pascal Jordan was his colleague from mathematics and physics. And together in 1925-26, they came up with this fundamental equation. Okay? This fundamental equation is that the momentum in quantum mechanics, the h bar, I must tell you, is h by 2 pi. And h is the Planck's constant. Okay? So this is the second fundamental equation that was written down. Earlier, you were very, very familiar, not with an equation, but with a proposal and a hypothesis, even though that was also called an equation. Okay? The 20, 30 years before, everybody knew of this from the hydrogen atom spectrum, from the emission spectrum of hydrogen atom. That the frequency is nu bar from n to n prime. This is what is called not the frequency, this is called the wave number, which is the number of waves per unit time or unit distance? Unit distance. What is the number of waves per unit time? That's frequency. Okay? What's the relation between the two? What's the relation between nu and the nu bar? This is per time. This is per length. What is it? You must get the right dimension. So, obviously, you multiply L by T. You will get isn't it? Sorry, T. Yeah. So what is C? C. Okay, field ball, right? Isn't it? L by T, multiply L by T. 1 by 2. So, dimension should lead you to understand some of the formulas right away, okay? You shouldn't worry about memorizing it if you know the formula is right or wrong. By checking, make sure that both sides are the same, okay? Now, what is this equation, by the way? You remember RH into 1 by N square N prime square. And when N is 1, it was known as a Balmer series, Lyman series. It was known as a Lyman series. When N is 2, it was called Balmer series. And this was already known. This was not a fundamental equation, but this was an observation of the entire spectrum of hydrogen, that the spectrum of hydrogen, absorption spectrum of, the emission spectrum of hydrogen could be fit by two numbers, two integers, okay, by different people. And therefore, Niels Bohr came up with a very beautiful model when he said that, like Planck, who said that the energy emitted by a particle is quantized, or the energy transaction by the material particle is quantized. Then Niels Bohr came up with the idea that the electron angular momentum, when it is going through an orbit, when it is rotating in an orbit, the electron A does not lose its energy. The fact that it is accelerating or decelerating still means the charged particle does not lose energy if it is in a state called the stationary orbits. And the stationary orbits were given the quantum numbers n equal to 1, 2, 3, based on the fact that the angular momentum of the electron in that orbit, MVR, is NH by 5. If the angular momentum fits that, the angular momentum is quantized. So, this was another famous equation, but this was not a derived equation. This was fit from the experiments. And obviously, Schrodinger at the time, who was quite old, I mean, Max Born was slightly older. I think he was in his late 30s, or probably, late 30s. But Heisenberg was in his late 20s when he discovered this equation, okay? When he put what is called the matrix formulation of quantum mechanics. He imagined Q and P were matrices, and therefore, when you take the product of two matrices, it is important in which order you multiply the matrices. And so you can see that if P is given by minus IH bar d by dq, and if you write PQ some function of Q, you see that the activity is going to be minus IH bar d by dq of Q psi of Q. So here obviously you have to use the relationship of the product derivatives, okay? This is a derivative. Therefore, the derivative gives you what? Minus IH bar psi of Q when you take the derivative with respect to Q. And if you take the derivative with respect to psi Q, you get minus IH bar Q d psi by dq. Therefore, now you can see that Q P psi of Q, if you write, that's going to give you Q minus IH bar d psi by dq. And so if you take the difference between the two, you see, it's not 1, it's not 0. If you take the difference between the two, obviously, this will become minus as is, okay? And so this goes away, this goes away, and so what is left over is PQ minus QP acting on any function psi gives you minus IH bar. I had earlier QP minus PQS plus IH bar, okay? But this is the same thing, you take the negative of that, okay? Now, therefore, it's irrelevant to me what this I is. Sorry, should have a psi here, yes, should be. Irrelevant to me, this quantity acts as though it is equivalent to minus IH bar when it acts on any function. So, quantum mechanics is no longer multiplication and simply identifying values for position and momentum, but position and momentum become what are called operators, because this is now operating on the function, acting on the function. So quantum mechanics came up with the idea that operators are important, and then later it was that all measurable quantities in any system are associated with Hermitian operators. Hermitian is a very special requirement for the operators. But anyway, those are getting into the details. What is important is the second most important equation was the one that I wrote down there.